Hi, in this video I'll be giving a demonstration of processing a large batch of direct infusion metabolomics data using AutoVectis. We'll start with a folder full of Bruker files and end up with each one of those assigned and a database combining all the results into one file. So as usual, we'll start with the AutoVectis splash screen. We're going to be processing Bruker files from the transients onwards, so we'll need to start in AutoVectis. Whenever you want to batch process files in AutoVectis, first of all you need to process a single file individually. So in the file path control, I'll select a single file from the folder that I intend to batch process. I'll keep the number of zero pads at the default value of 2. But I know that this file and others in the batch have harmonics, so I'm going to raise the minimum mass to 150. And the metabolites in this file tend to be rather small, so I'm going to drop the maximum mass down to 1 kilodalton. I'll keep the default apodization settings of dpac and an F of 0.5. But I'll change the phasing mode to recalculate, which means that AutoVectis will attempt to solve the phase correction function using only information in the spectrum. And now we're ready to phase this file, so I'll hit begin. So the data is loaded and peaks for phasing are selected, and then a brute force fit is applied to a small region. AutoVectis normally does a good job of identifying the right peaks, identifying a suitable region for brute force fitting, and then a good job of doing that brute force fitting itself. So all we need to do is hit accept. Then the system will extend the initial fit over the complete spectrum. And there we have our absorption mode spectrum, and we can go ahead and detect the peaks in that. Within the AutoPeaker peak picking tool, you can zoom in to see the thresholds that are used for peak picking. If needed, you can change the signal to noise ratio required for a peak to be detected using the SNR control. But in this case, we'll keep it at the default value of 3. So now we've identified the correct settings to phase a single spectrum in the batch, we can go ahead and set up the batch run, which we do on the Batch Process tab. There are a number of different batch processing options available on this tab, but the one we want just now is Phase All Files in Folder. When this dialog opens, the file list will contain all the files that are in the same folder that the original file was in. You can edit this list if there's files you don't want to include in the batch process, or you could even move to a different folder and process the files in that folder. And underneath the list of files, we need to look at the phasing mode. The default setting is use current phase correction function. This means that for all the files in the batch, AutoVectis will use the current phase correction function as the basis and then re-optimize that for each individual file. And we'll just stick with this default setting. So we're sticking with the complete recommended batch and the default settings, and then to start this batch running, we just click Run Batch. And then for each of the 93 files in this batch, AutoVectis will load the file, convert it to absorption mode, detect the peaks, and then save a TDMS file that's suitable for onwards processing in Autologous. It's going to take about 10 seconds per file in this batch, so I'll speed it up and then jump to the end of the process. About 12 minutes have passed and we're nearly at the end of the batch run. You can see how many files are left to process here. And now we're on to the final file. And so the number of files left reads 0 and the begin button is flashing, and that means the batch process is finished. The parameters used for phasing each file into absorption mode are stored in a table on the MS Image tab. The contents of this table are also saved to a text file, which you can keep for record's sake, and you can use to identify if the phasing for each of the files in the batch is likely to have been successful, without having to manually review each one. But now the batch processing is complete, we can close down AutoVectis and go back to the main splash screen. Now we want to assign the contents of all of those files, and we'll do that using Autologous. Autologous offers a number of different workflows for assigning elemental compositions to peaks in a variety of complex spectra. As here we want to process a batch of files, we'll be using the batch workflows down here. And the first workflow we need is batch recal. The batch recalibrator tool lets us apply polynomial internal recalibrations to batches of files. So first we need to tell it where the batch is located. Next we need to identify a ref file that contains a list of the potential ionic formulae that could be used to internally recalibrate this batch of files. Normally this file is built up by manually processing a subset of the files in the batch, and then identifying common components that could be used for recalibration through the entire batch. Not all of the components need to be found in all of the files, because the batch recalibrator tool will intelligently decide which peaks to include or not include in the recalibration function. But for this demo, we'll just use this file that I created previously. Here you can see a list of all the potential recalibration ions on the left, and a list of all the selected batch files on the right. Before running the complete batch, it's worthwhile testing the settings and the internal recalibration formulae on a few individual files in the batch. If you double-click on any member of the batch, then the system will test recalibrate just that file. That looks successful, so let's try another one. That also looks good, but let's just try one more. So it looks like the recalibration peaks and the search range settings are fine, so we can go ahead and click Run Batch. So now the batch recalibrator tool will load and internally recalibrate each of the files in the batch, and then resave a recalibrated version into the batch folder. The original uncalibrated file is also kept and just moved into a subsidiary folder. As we have almost 100 files to recalibrate, I've sped up the process so that we can get on to the next stage faster. Each recalibration curve is presented to the user, so they can, if they wish, watch them as they're generated to check for any anomalies. But a file is saved at the end of the batch recalibration process that contains all of the internal recalibration parameters, as well as a series of figures of merit that can be used to judge whether or not it's likely that each file has been recalibrated correctly. And this file can be kept for records purposes as well, or for retrospective audit. And once the batch is complete, you can see it save the audit file. And then the batch recalibrator tool closes down and takes you back to the main autologous menu. So to recap, we used AutoVectis to convert a batch of Bruker files to absorption mode, and then we've used the batch recalibrator tool here in autologous to internally recalibrate them all. So now we've reached the stage where we can assign identities to the peaks in the files. If this was a dissolved organic matter or petroleomics type file, then we could use the many homologous series in the sample to help us build up an inference network that we could use to assign formulae to the peaks. But as this is metabolomics data, those long homologous series don't exist in this case. So we'll assign the peaks in these files using their accurate mass and their isotopic fine structure using a tool we call light mode. You can apply light mode to individual files here, but we're going to be applying it to a batch, so we'll use the batch light mode option. And the first thing we have to tell it is where the batch is. And then the system will import all the TDMS files in that folder. We could edit this list to remove files from the batch processing, but in this case we'll keep the whole list and just click Generate File List to start the batch process. And this opens up the light mode window. On this window we can define all the assignment parameters that will be used for the first file and all the subsequent files in the batch. In these top two controls we can define the maximum and minimum stoichiometry for all the required elements. And then underneath we can define the acceptable mass error range. And we need to define the type of ions that we might see in the data. We could type the ion types directly into the control, or we can use the drop-down list to import common combinations. This is negative electrospray data, so we'll use the common negative ions list. These checkboxes also include useful controls. Using the validity checks applies the kind and fine rules to ensure that the chemical formulae generated are broadly plausible. Check isotopic distributions means that the relative ion abundance and the isotopic fine structure will be used to help rank assignments. When fast mode is turned on, isotopic distributions are calculated using a much more rapid polynomial method, and when it's turned off, a modified version of the Mercury algorithm is used. For small molecules like metabolites, the fast mode is appropriate. When the Keep Existing Assignments box is checked, then any existing assignments will be kept. But when it's off, the file will be reassigned from afresh. And finally, when Consider Mass Accuracy is turned on, that means that the mass accuracy of the monoisotopic and all the isotopic peaks are considered as part of the way the algorithm ranks which assignments are most likely for each individual peak. For this batch run, we'll keep all of these options turned on. For some applications, you may not want or need to assign all the peaks in the files. Peaks are assigned from the most intense peak downwards. So we'll set up this batch run to assign only the most intense 500 components within each sample. And when a component is assigned, it's not only the monoisotopic peak that's assigned, but also all of the isotope peaks, so we will in practice be assigning more than 500 peaks per spectrum. If you want light mode to attempt to assign all the peaks in the file, then you can set this to 0. Finally, it can often be useful to request that the system prefers assignments which use smaller numbers or combinations of heteroatoms. And we can turn that on with this checkbox. Now we've assigned all the parameters that the system needs for assignment, so we can run light mode. As components are assigned, their mass error is plotted on the mass error plot. And we can keep track of how many components have been assigned in each file using this indicator. When I ran this demonstration run, it took 1.5 minutes to assign each file, and we have almost 100 files in the batch, so it's going to take a while to finish, and rather than sitting here watching it, I will speed up a little bit and then jump to near the end of the run. So I've jumped to the end of the batch, where the system is assigning the last file. And once the batch is complete, Autologous returns us to the main menu. And so now we come to the last part of the batch workflow. By this stage we have 93 assigned files, and we could go in and review the results of each one of those individually using this module. But we can also bring all those files together and produce a single output table that shows how the intensity of each component varied across the entire batch. And we do that using the batch results module. As is normal, the first thing we have to do is tell it where the batch is. We could edit this list, but just now let's just keep it complete. Autologous will save the combined results in two different file formats. One of these files will be an SQLite database that will contain a table of the results from each individual file and another table of the combined results showing how each component will vary across the complete run. In this dialog box, you are defining what that database will be called and where it will be saved. We chose this SQLite file format because it's easy to browse using openly accessible SQLite file browsers and is commonly used in bioinformatics. Like most common programming languages, Python and R both contain libraries that allow them to search, open, and edit SQLite databases. But the Autologous batch extractor will also export the complete file table as an Excel file. And it will be saved with the same name and in the same location as you selected for the SQLite database. And that's the batch processing complete. So in this demo we've gone from a folder containing almost 100 Bruker direct infusion metabolomics files, and we've processed them through absorption mode, batch recalibration, batch assignment, and finally combining all the results into a single database file, all using AutoVectis. So I hope this demonstration of some of the batch processing capabilities of AutoVectis has been useful. And as always, if you have any questions, you can contact us at autovectis@gmail.com, or you can speak to one of the SpectraSwiss team directly.